Hey guys, it's Ms. Johnson and I'm here to talk to you guys today about Section 2.2. Section 2.2 is the first introduction into normal distribution, and normal distribution is something that we're going to use very heavily in this class throughout the rest of the year, basically. So this section is broken into 3 different pieces. So this is just the first of 3 pieces of Section 2.2. We're going to start off talking about density curves. So when we talked about quantitative data back in chapter 1, we looked at a bunch of different ways to graph it. We talked about dot plots, we talked about histograms, we talked about stem and leaf plots. There's a lot of different ways to make a graphical representation of quantitative data, okay? What we want to get into in section 2.2 is turning that data into a density curve, okay? So when we explore our quantitative data, we want to plot the data. We want to make a graph. Sometimes most of the time it's a dot plot. That's usually the easiest one to make, and it's the most applicable, I think. It retains the original data set, which is nice too. You can make a stem plot, you can make a histogram. You want to look at the overall pattern. You want to describe the distribution. When we describe that distribution, it's that SOX acronym where we have shape, outliers, center, and spread. And then look for the departures from the data or weird patterns. Calculate the numerical summaries. That's what we do in our calculator most of the time, but we get that 5-number summary of the median and the Q1 and the Q3 and the min and the max, and then we also get the mean and the standard deviation, which go together. So those are all the summary statistics that you'll get when you plug all that data in. And then that step number 4, that's where we're going to introduce a new element into analyzing this type of data. We are going to describe the data by drawing a density curve. We'll draw a density curve to help model the data, and it's different than a graph. It seems like they're the same thing, but it's a little bit different, okay? So we're going to talk a little bit about density curves. Density curves, it's a curve that is on or above the horizontal axis. You're usually living in quadrant 1 here. It's very rare that we have negative values in our data. That doesn't mean it's impossible, but it's rare. You're certainly not going to have negative frequency or negative relative frequency. So you're always going to be in either quadrant 1 or 2. Most of the time it's just quadrant 1. But the thing about a density curve, the one thing you want to remember is that your density curve houses 100% of your data. All of your data lives under the density curve. So when it says it has an area of exactly 1, that's because all of the data lives underneath that density curve, okay? So it says the area under the curve and above any interval of values on the horizontal axis estimates the proportion of all observations that fall in that interval. So if I wanted to look at this graph right here, here's the dot plot. This is the dot plot, okay? They took this dot plot and they turned it into a density curve. It says the overall pattern of this dot plot of the amount of time that it took Selena to get to the bookstore by train is in this dot plot. Now you take that dot plot and you turn it into a density curve. It's never a perfect translation. We've talked about this lots of times in this class, how data is messy, it's raw, it's not always neat and pretty. So if you look at that dot plot on the left, you can see that it's not perfect square, but it is a mostly uniform. I would call this uniform, okay? So this is a uniform distribution, and this appears to be mostly uniform. There's not a lot of places that are really, really far off from the overall kind of flat line of these, okay? So you can see that her journey time in minutes, 2 minutes, 2.5 minutes, 3, 3.5, 4, 4.5, 5. If I wanted to find the proportion of values that go from 4 to 5, you'd treat this like area. Think back to geometry. This is just a rectangle. In this case, okay, even if it's not a uniform distribution, you can still just treat this as area. This is just area under a curve. And you know that the total area is 1/3. But the total area is 1. But the height of this, if you look at the height of this curve is 1/3. So I know that over here I'm also at 1/3 because it's a uniform distribution. And here I went from 4 to 5. which is 1. So I'd have area equals 1 times 1/3, which is just area equals 1/3. So a third of the time, she waits from 4 to 5 minutes, okay? The density curve, you got to think of this as area. So it says a density curve has area exactly 1 underneath. Now, not all distributions are uniform like the one we just looked at. In this one, I've got more of what we will come to learn as normal distribution curve here. In this, it says the overall pattern of this histogram of the scores of 947 7th grade students in Gary, Indiana, on the ITBS vocab test can be described by a smooth curve drawn through the tops of the bars. So the bars are the purple things. That's the histogram of the kids' scores. What they did is they turned this into a density curve, and by turning it into a density curve, it has this smooth shape. Now, again, you can see it's not a perfectly perfect translation, but it gives you a good picture. And we're going to look at normal curves a lot in this class, and that's going to be a picture that you're going to get used to drawing. All right, so let's just talk about how we would read density curves if we were looking at them. It says a density curve is an idealized description of the distribution of data. Did you like that? Idealized description. If our data was pretty and smooth and nice, this is what it would look like. That's basically what they're saying there. We distinguish between the mean and the standard deviation of the density curve and the mean and the standard deviation computed by the actual observations. So there is a little bit of a difference. The usual notation for the mean of the density curve is mu, and we write the standard deviation as sigma. So that mu, it has like a tail in front of a U. So if you're trying to write that out yourself, it's like a tail in front of the U. The sigma is kind of like you drop down and make a little loop backwards, okay? So mu and sigma. This is population. This is mean of the population. This is standard deviation of the population, okay? So that's why they say this is an idealized description, because if we're talking about the entire population altogether, this is how it would look. We're hoping that it would be this pretty nice thing, okay? And when we get into mean of the population and standard deviation of the population, we're talking about the Greek letters. And that's versus if we were talking about the, sorry, my thing's trying to pick a bunch of different colors. If we were talking about just the data, if we're just looking at the data that we computed the summary statistics of, then we are looking at X bar for mean of a sample. That's called a sample. Or S of X, which is the standard deviation of a sample. Okay. Now, we've talked before about how it's really, really hard to get the whole population mean and the whole population standard deviation. But when we're looking at a density curve, we're looking at the idealized description. So that's why we kind of talk in these bigger terms over here. One other note I wanted to make about the two density curves that you see at the top of this slide is just the fact that this curve right here that appears to be symmetric with one peak, that is a curve where the median and the mean are in the same place. The median is right over the mean when you're looking at a symmetric distribution. When you look at this distribution right here, which is skewed to the right, this has a right-sided tail. Notice that the mean is trending above the median. The mean is above the median here. And that's because your mean, remember that mean is the least restrictive one. It's the one that's not restrained. So the mean is gonna follow the tail. So when you have a right skewed distribution, your mean is gonna be above your median in the density curve. Okay, so now let's get into the real nitty gritty here. This is the really important part of this section. So we talked about density curves. They have an area underneath of 1. They can be used to kind of represent an idealized viewpoint or picture of the data of the population. But then a lot of those density curves are what we call normal curves. And normal curves are when we have a symmetric shape that fit that kind of bell-shaped distribution. Those of you who are taking AP Psych, you're gonna talk about this shape of distribution. I think they call it the bell curve, but you're gonna talk about normal distributions in your AP Psych class. So it says one particularly important family is the normal curves. That's what we use when we're describing normal distribution. The shape of all normal distributions, they have approximately the same shape. They're symmetric, they have a single peak, and they're bell. They could be shorter, they could be taller. Like this one's really short, this one's a lot taller. It just depends on how the data falls. But if there's one peak roughly in the middle, and then the data fans out from there, you've got a normal curve. The center, the mean, the mu, if you will, that's red mu, if I didn't say that on the other side. Mu is located at the midpoint of the symmetric density curve, and it's the same as the median. Mu and median, mean and median are going to be the same in a normal distribution. And then variability, standard deviation is what we use to measure the variability, because we are typically talking in terms of the mean. The mean is always the center of our normal distribution. And then when we speak in terms of mean, we are then talking about standard deviation. Okay, so one thing that I want you to recognize, when we draw this normal curve, like you see, okay, there is a point, and by the way, I think I've mentioned this before, but this test is not a drawing test. You will draw normal curves on this test, okay, if on the AP exam, I mean. You will draw normal curves, I can promise you that. It's not a drawing test. Your pictures don't have to be perfect as long as you label them accurately. But one thing I want to point out, okay, this point right here, see that point right there? If you think back to science or even geometry, this is the point in the curve where it goes from being concave down to concave up, okay? Do you see how I'm concave down? All right, that green is kind of hard to say, or see. Concave down, and then this is concave up. Okay, that point right there that marks the switch in those two shapes, that marks your +1 standard deviation. Okay, the same thing on the other side. The point where you go from concave up to concave down, that marks your -1 standard deviation. You have to think of this as a number line where the mean is at 0, because the mean is 0 standard deviations away from the mean, if that makes sense. So then if you go +1 standard deviation, you're at the point where that graph changes directions. If you go -1 standard deviation, you're at the point where that graph changes directions. And another fun fact about those is they are at the exact same height in a normal distribution. Okay, that's not a coincidence. They are exactly the same width from the mean because you're using the same standard deviation, you're just going in the other direction. And they are at the exact same height on the curve, okay? So if you look at it here, here's that one. If I go straight across, that's the -1 standard deviation, okay? So that's just kind of a fun tip about drawing your normal curves. When you have a hard time placing where your standard deviation is, that's where you know you can put it. All right, a normal distribution is described by a symmetric single-peak bell-shaped density curve called a normal curve. Any normal distribution is completely specified by two numbers. We work with the mean and we work with the standard deviation, okay? Why are normal distributions so important? Here are 3 reasons that we use normal distributions a lot. Normal distributions are good descriptions for some distributions of real data. Distributions that are often close to normal include scores on an SAT or an ACT, repeated careful measurements of the same quantity, like somebody who might be doing quality control at a tennis ball factory, characteristics of biological populations, so length of crickets, yields of corn, anything like that that's growing, we're typically going to see a normal curve. Normal distributions are good approximations to the results of many kinds of chance outcomes, like the proportion of heads in many tosses of a fair coin or rolling a certain number on a number cube. You're going to get into inference methods in chapters 8 through 12 of our book, where we're going to be basically only sticking in normal distributions. Okay, so one thing that is also a fun fact about the normal distribution, the normal curve, the standard deviations mark a specific piece of the data. So when you are in the middle, there's your mean. That's 0 standard deviations away from the mean. That's why it's marked with a 0. When you go 1 standard deviation in either direction, you have approximately 68% of your data. When you go 2 standard deviations in either direction, you have 95% of your data. And when you go 3 standard deviations away from your mean in either direction, you have 99.7% of the data. That's where that curve falls really flat. There's not a whole lot of area underneath the curve out here beyond 3 standard deviations. Okay, that's why it only amounts to be 0.3% of the data. So, most of the data that we look at is going to be between or within 3 standard deviations either direction of the mean. This thing right here, this 68, 95, 99.7 is also called the empirical rule. Empirical rule. You'll see it referred to that sometimes. The empirical rule is what tells you you've got 68, 95, 99.7, or in other words, you're looking at a normal distribution. Okay, so the thing about the empirical rule is that this only applies to normal distributions. If you're looking at a skewed curve, I didn't draw that very well. Let's try that again. How about this? Whee. There we go. Skewed curve. Your mean is going to fall somewhere. Your median's going to be right about here, but your mean's probably going to be about here. So let's say this is your mean. If I go 1 standard deviation away, I might be up here. If I go 1 standard deviation in the other direction, I might be here. You can't use the empirical rule on this. This is not going to be 68% of the data. You don't know what that percentage is going to be. It only works for normal distributions. So it's just one thing to keep in mind. You have to have a symmetric and normal distribution before you can use the empirical rule and before you can do any further calculations with that. And that's an important thing because often when we get later into this class, our first task is going to be, show me that it's normal. Prove that it's normal, and if it's normal enough, if you can qualify it as normal enough, then you can do all of the analysis that we can when we have a normal distribution. All right, so that's the end of our first part of our notes for today, the very first introduction to normal curves. Thanks for listening, and I will catch you for part 2 next time.